Hello, everyone. I'm Wes Purvis, and I'm going to talk about Wi-Fi. So 6 gigahertz is here. We are shipping our products. This is our product portfolio. We have an AP45, which is our flagship AP, tri-band, supports still 5 gigahertz. AP34, not yet shipping, but shipping very soon. And that is our cost optimized 2x2, no dual 5, no VBLE. So that's what we have. I want to talk about what we've done with it so far. So we have been shipping. We have now a whole bunch of AP45 deployments with 6 gigahertz. It's actually interesting. There's a decent number of people that are just buying the AP and not turning on 6 gigahertz yet. There are some people that just go ahead and turn it on, and so it's interesting to watch that dynamic. Here is a deployment. This particular deployment had enough APs to use all of your 6 gigahertz spectrum using 80 megahertz channels, because we're still recommending 80 megahertz as a default channel width to line up with using primary scan channels. And here is what radio resource management did at another customer. This is channel distribution. So 6 gigahertz RRM is alive, well, and working very well. We're definitely still learning and tweaking. Things aren't perfect, but they're in really good shape. I think 6 gigahertz in general is going to kind of change the way that we approach deploying Wi-Fi to some extent, right? And I'll talk a little bit why. Right? There's a couple of reasons. And first you got to think about clients. So there are some clients out there, and it's growing. So there's a pretty healthy contingent of Windows clients out there. And funny enough, I went to a Best Buy store a few weeks ago because I was frustrated. I wanted to buy some clients, and I couldn't find online which clients, which of their clients actually supported 6 gigahertz. So I went to a store and I literally went to every single laptop and looked at the network adapter that was in there. And I would say about 20 to 30% of the clients supported 6 gigahertz, which was, I was pleasantly surprised, right? So that's just the Windows clients. I didn't look at the phones or obviously the Mac don't support it. But from a Windows perspective, right, and I mostly saw AX211 in there, some AX210s. The 211 is built into the motherboard. The 210 is the discrete card. And then some MediaTek chipsets as well. There's a Qualcomm chip that you'll probably find. It's not as common in the Windows machines, but it is out there. There are some HP machines that have it. This HP EliteBook has the Qualcomm, and then there's a bunch of smartphones out there. It started with the S21 Ultra at the beginning of 2021, and phones are getting introduced. So the notable exception here is, where's Apple, where's iOS, where's Mac OS? Hopefully they come soon. Next announcement is in September. So let's see what happens there. And that will kind of, probably kickstart the 6 gigahertz ecosystem, more so than it already is. So let's talk about deployment considerations. The first one is security. Right, so as I'm sure most people are aware, when you deploy 6 gigahertz, you are only allowed to use WPA3 or OWE. There's no open, there's no WPA2. You have to move to WPA3 or OWE. So that creates some considerations that you may want to think about. You may not be ready to move to WPA3. So here is some testing that we have done around using various security types between different APs. Right, so this is, for use cases where you may want to put in some new APs, or you want to use a transition mode. So here's kind of what we see. If you're using OWE, there is no roaming, as you can imagine, between open. Same thing with OWE transition. It just doesn't work, right? So once you bite the bullet of moving probably your guest network to OWE or OWE transition, just know that if you have, open, that same SSID name broadcasting is open, you're not going to have a good roaming experience. You're going to want to use a different name. From a WPA2 personal and WPA3 personal standpoint, there is not a good roaming experience between WPA2 and WPA3 personal because they're so different under the hood. Now, if you do WPA3 transition and you're connected with WPA3, when you roam between WPA3 only SSID or BSSID, you will have good mobility. So just something to think about. If you're now probably if you're a client that supports 6 gigahertz, you're going to support WPA3. If you're connected on 5 gigahertz, you'll also connect on a transition network in WPA3. But I think the most relevant for, at least for a lot of our customers is enterprise. And the good news is under the covers, WPA3 enterprise and WPA2 enterprise are fairly similar. You add management frame protection and there's a couple other changes, but not major ones. So you actually do roam well between WPA2 enterprise and WPA3 enterprise. So we kind of think there's the least risk in moving to straight up WPA3 enterprise. Some customers may want to think about transition. The good thing about transition is it's transition. It makes life easier to move to WPA3, but then you have to worry about transition. And probably if you turn on transition, you're not likely to turn it off in the future. So just a note on transition, how we're implementing transition mode. So we will allow you to configure WPA3 transition on a 6 gigahertz SSID, or an SSID, a multi-band SSID, I should say, with 6 gigahertz on that SSID. And so what we're actually going to do is in 2.4 and 5 gigahertz, we will broadcast transition mode. In 6 gigahertz, we will broadcast WPA3 only or OWE only. Right. So we did some smarts under the covers to allow you to have a single SSID. We thought that's important because when you're looking at your statistics and your monitoring, it'll show up as a single SSID, within your reporting, as opposed to 2 different SSIDs with the same name. And it will allow fast roaming to work. So usually when you have 2 different SSIDs with the same name, you don't fast roam because the keys aren't shared. So this is an option that we have, or this is a capability that we have that we think will make using a transition mode easier. Now, what are your options when you think about your SSIDs that you currently have? Right. So if you want to roll out 6 gigahertz, pretty much your options are you can spin up a new SSID that's 6 gigahertz only. And that's probably the path of least resistance. But then you have to have either via MDM or your clients need to know to use this SSID. I think more commonly you'll see band specific SSIDs where you maybe do a 5+6, and then you have maybe a 2.4 and 5 where you have if you've already split up your SSIDs, you can use that same strategy where you have a fast and a slow, or the name. Some people put 5 and 2.4 in the nomenclature. Well, now you have 6, so maybe you just accept that. You bite the bullet and just move to WPA3, and you have you use your existing set of SSIDs. This is the cleanest, but it's probably also the most challenging. You need to understand your client base and the type of clients that you're using, and I think also the type of SSID it is, right? So personal, WPA3 personal is a little bit more difficult to move to than WPA3 enterprise, in my opinion. WPA3 enterprise, from what we've seen, is clients just kind of work, are natively supporting it. You can turn on transition mode for your existing SSIDs. I think folks will probably mostly do that, if I was to guess. But then you have to think about edge roam, right? Like this is the especially in higher ed, this is kind of the unique case where you can't change your SSID name. So if you want to turn on edge roam in 6 gigahertz, you need to support WPA3, whether you do transition, whether you do WPA3 only. I know edge roam has some guidance out there, but I think this is one that I think this is one that folks will kind of need to internalize themselves and figure out what's best for their institution. Okay, so let's just quickly pause on where we are with client support on WPA3 and OWE. So from the WPA3 perspective, enterprise and personal support is pretty good across the board. You have it on Android, you have it on Apple, iOS, macOS, Windows, and Chrome OS, right? So pretty good. From an OWE perspective, it's not as good. And notably, Apple, iOS, macOS does not support OWE. Android does, Windows does, Chrome OS, actually not sure. But yeah, from a WPA3 perspective, pretty good support. And we've done deployments now with WPA3. This is a WPA3 personal. This was an event that was put on, and so probably newer client devices, mobile phones, mostly. There were some laptops, but about 80% of the clients natively supported WPA3 personal on a WPA3 transition SSID. So 80% connected with WPA3, 20% connected with WPA2, and a handful, less than 0.5% didn't connect at all. Right, so that's always the risk. Those were older Android clients, so you're like Android 9 and 8, like those ones and older, as well as some Microsoft Surface laptops that with some Marvell chips in them that just were not happy. Beyond those, in this 12,000 clients here, all got on happily. From a WPA3 enterprise perspective, we see similar adoption. So yeah, most clients, especially if they're relatively recent right now, if you're in a specialty vertical, if you're in healthcare and retail, logistics, you may have older devices where this may not be true. And so you'll probably want to have, keep a legacy SSID where you may have already had a legacy SSID anyway. So you can spin up a new, future SSID, if you will. So that's like security. Keith?
Before you go on, you mentioned a lot of options for removing your SSIDs. What's your recommendation?
So my recommendation would be to move to WPA3 only and be done with it, right? But that's not realistic. So I think the transition mode is kind of the easiest, right? If you want to use your existing SSID names, you need to do WPA3 transition, because that way you will, it's very low effort to turn on 6 gig. We don't turn on 6 gig by default, actually. So you have to go into the SSID and enable it. Once you enable 6 gig, if you have WPA2, we'll tell you that's not allowed. You have to configure WPA3. And so I think from that perspective, the easiest way is to do transition. I don't like transition, because you're probably not going to ever get away from transition, but I think it's the most realistic. Okay, let's talk a little bit about design. And so we have deployments now. So over the past few months, we had been talking about what we think things should look like. Now we can talk about what things do look like. So from a coverage standpoint, right? This is a test where we had 5 gigahertz and 6 gigahertz configured at the same transmit power, so 8 dBm in mist, and 5 gigahertz we were configured at the very low end of the spectrum, channel 36, and 6 gig configured at the very high end of 6 gig. So that's the biggest gap. That should be the biggest difference that you'll see. And actually, we saw very little difference. So this is just one data point, but looking around, usually 0, 1, 2, 3, a very small amount of difference between 5 and 6 gig. So if you have a good transmitter and consequently a good receiver, right? We've seen sometimes when I went to the Best Buy store, I bought 2 laptops. One of them heard 6 gigahertz very well. The other one did not hear 6 gigahertz very well, and I returned that one.
If I may, how are you actually getting 6 gigahertz data into Ekahau? Because to the best of my knowledge, that's not something that we can.
Okay.
A friendly relationship.
Okay, I have real trouble believing that the coverage is the same. Given,
as do I, which is why I asked the question.
Right.
Right. I mean, so, it's a little incredulous.
Yep.
Right.
So yep.
Talk a little bit more.
I will. Yes. I have a story that I'm building to.
Oh, okay, good. Okay.
So yeah, and remember, this is downstream, right? This is from the client perspective, and so when you have a good receiver, line of sight, you can hear 5 gig, 6 gig pretty similarly. You'll start to see differences when you move to non-line of sight, because there's different attenuation values as you go through different material types. And so here's a client. From the client perspective, you have, on the left is a little blurry, but that left is 5 gigahertz. It says channel 36 in the red box, and the signal quality is 84%. On the right is a 6 gig laptop. on channel 197. Signal quality is 95%. So sorry, 85%, actually 1% better in this case. So from this perspective, coverage is very similar. Where it starts to fall apart is when you look at uplink. And so clients in the low power indoor mode and standard power mode actually are transit power constrained. The box should be around asymmetric uplink and around 6 gigahertz, right? So what this is saying in our coverage SLE, we're seeing asymmetry in the link, meaning that the uplink transit power, the uplink data rates that are being used are lower than the downstream data rates because clients are transit power constrained in low power indoor mode. Here's another visualization of it, right? So this is to your point of, so on the right, the blue line is AP side, meaning that's how the AP hears the client, also known as uplink. The red line is client side. That's how the client hears the AP. So also known as downstream. So the red line, downstream, good signal strength. The blue line is, for this particular client, significantly lower in the upstream direction. And this is something that we see sort of across the board, right? Generally, the limiting factor here is not the downstream direction, it's the upstream and the transit power that the clients are allowed to use.
Is this impacting the user experience? Do you see anything coming back from the SLEs? Yeah,
so that's actually, like, that's what I'm showing here, right? We detected asymmetric, coverage, coverage SLE, asymmetric uplink. Now, from a user perspective, right, it just means that you got to stay a little bit closer, right? As you get to the edges of your cell, right, your cell edge is going to be a little bit smaller. That's kind of what we're thinking here.
How does this data impact your RRM? Are we going to see now APs increase their transmit power because you're seeing that uplink difference there?
So that gets me to my putting it together slide. So thank you. So the signal difference between 5 gig and 6 gigahertz varies based on the data, on how you collect the data. We've collected a whole bunch of data. We've seen widely varying results. But I think we're at a point where we're ready to make a stake in the ground, which is in the downstream direction, pretty similar coverage. In line of sight, non-line of sight, you'll start to see some differences, as I mentioned. But upstream is where the restriction is or where limitation is. And so from a downstream direction, RRM can fix that, right? We can boost the transit power. And you'll actually see so far, what we've seen so far is 6 gig is 1 to 2 to 3 dB higher than 5 gig from an RRM power perspective. But we can't fix upstream. So upstream comes down to design. So our conclusion is 6 gigahertz requires higher AP density and smaller AP cells. Likely, if you have a capacity-based 5 gigahertz design, that may be okay, but you'll probably want to evaluate and actually put some thought into it.
Okay, so you recommended earlier an 80 megahertz channel. So if in the 6 gigahertz band, I'm able to operate with a wider bandwidth, I can operate data at a higher data rate. So if I compromise my data rate and transmit at a lower data rate, can I then recover the coverage and therefore match my 5 gig and 6 gig coverage? See what I'm saying?
So I don't think it'll play out like that. So if you change your channel bandwidth, what you've done is you've increased the maximum transfer power that you're allowed to use.
That's true.
Right? Doesn't say that you necessarily have to use it, but the maximum that you're allowed to use. And clients are still limited as to what they can use, right? They're limited to -1 dBm per megahertz. So you do see a bump as in the US at least. And so I should caveat by saying in worldwide, in like Europe, your client transfer power is higher. So US, you're going to see, probably a bigger impact than in Europe.
So I can't say my minimum data rate in the 5 gig is like 12 megabits per second, but my minimum data rate in the 6 gig is 6 megabits per second, and therefore match out my coverage that way.
From a configuration perspective, you can.
Right, but it doesn't work.
I don't think it'll get you. Like, I guess it's not something that we've experimented with. Typically, especially like when you comparison I'll make is between 2.4 and 5. We'll typically use the same data rates in 2.4 and 5.
Right.
Thanks, Wes. I just want to clarify some of the data that we saw. So you had the floor plans up and then the screenshot with the Windows laptops. I was just curious, one, those Windows laptops were the ones that were doing you're taking the measurements with? And
They were not.
They were not. It's different. And I was going to ask if you then, in your testing that you're seeing, like we know that, like what a MacBook or like a higher end laptop sees is quite a bit different than what you see like on an iPhone or an Android. Are you seeing a similar delta?
Yep.
Or a more pronounced delta with the 6 gigahertz?
So I didn't put all the data in here.
Yeah.
But we've tested with a whole bunch of client types, and it kind of varies by the device. Again, there's different devices have, I think, different antenna characteristics, and I think the antenna is actually what's impacting the most. So from a mobile phone perspective, some of them they see 5 gig and 6 gig pretty similarly. Some of them do not see 5 and 6 gig pretty similarly, but all of them have upstream transmit power limits.
Yeah. Okay. Thank you.
And then just to clarify, this testing was all at 80 megahertz?
We've done testing over bandwidth. So we've done testing over channels. We've done testing over bandwidth. We've done testing over transmit power. So the data that I'm specifically showing that I showed was at 80 megahertz, but the summary in here includes all sorts of a mix mash of data.
Okay, so we'd be at the better end of that at 80 megahertz versus 20 megahertz in a dB difference, right?
Yep. Okay, so the last thing that I'm going to talk about from a 6 gig perspective is the importance of out-of-band discovery. And this is so to the 80 megahertz point, right? Today, the recommendation from vendors, MIST included, is to use 80 megahertz channels because those line up with the preferred scan channels, right? So the recommendation is to use preferred scan channels because it helps clients discover 6 gigahertz networks more easily. But what I'm going to show here is that this guidance may potentially change in the future. And the reason that we have this guidance now is we don't fully know all of the clients that are out there and the ones that will come in the future. But from the clients that we've tested, we have seen pretty good results with the reduced neighbor report. So as a summary, here are kind of your options for discovering 6 gig. Right? There's in-band, there's out-of-band. From an out-of-band perspective, you're most likely using the reduced neighbor report. From an in-band perspective, you can passively scan. You may see fills where you're sending basically a packet every 20 milliseconds. This is really meant for 6 gigahertz only APs where you don't have anything broadcasting in 5 and 2.4. You can do the AP can send an unsolicited probe response, and then from an active standpoint, on the PSCs, the client is able to probe. All that assumes that clients are looking at 6 gig. From what I've seen so far, without R&R, clients aren't really looking at 6 gig. So just as a summary, the reduced neighbor report is part of, you'll see it in probe responses as well as the beacon. This is from Beacon. For those of you that have a Wi-Fi scan tool, I have an AP set up in the back of the room. If you want to see what an R&R looks like in the 5 gig, I'm sure you'll be able to find which AP it is, which SSID name. And so there's a couple of important pieces of information that the client uses for discovering 6 gigahertz. Right. So one is the operating class, that's the channel bandwidth. 133 is 80 megahertz. The channel, so channel 37 in this case, the BSSID that you should be looking for. There's the short SSID, which is an SSID hash, basically. To hash your SSID to a common format. And then there's some other parameters in here, like is the AP co-located? Is it the same SSID? So all these help clients discover 6 gigahertz, and the way that the R&R is instrumented and how many APs you're putting in the R&R will vary by vendor. And we're certainly figuring out what's best. We are currently populating for co-located APs, 5 gig and 6 gig. So if you have a tri-band SSID, you'll see in 2.4 and 5, you'll see the 6 gig, the 6 gig SSID. For single band SSIDs where you have like 2.4 and 5, and a separate 6 gig SSID, you'll see that 6 gig SSID in those 2.4 and 5. So we always want to make sure that at least one 2.4, if enabled, at least one 5 gig BSSID for every 6 gig SSID is included in the RNR.
Wes,
Yep.
is that something you need to configure yourself, or is that automatically?
No, that's automatically configured for MIST. And then we also have implemented, but we have not currently enabled using RNR for neighbor APs. So that adds a whole new dimension. And we're starting with just co-located APs for now, but we may start doing neighbor APs in the future. We think, from a discovery and roaming perspective, clients will use the RNR for discovery and use 11K, 11V for roaming. So just some examples. So I did some testing without RNR and with RNR. And if you compare, basically without the RNR, it took this Windows laptop about 20 to 30 seconds to discover a 6 gigahertz only SSID. With 5 gigahertz, with the reduced neighbor report, it took less than 5 seconds to discover that 6 gigahertz only BSSID. It's hard to see, sorry, but just an amazing difference. Like, it pretty much makes 6 gigahertz useful. And I've seen this with the clients that are out there. So the Android clients that are out there, the Windows clients that are out there, they behave similar. That the RNR is important for 6 gig delivery. And kind of my last point in here is that so regarding the preferred scan channels. No, I didn't update the text. I just copied the slide. But really, so when you're from when an AP is on a PSC or an AP that's not on a PSC, we're seeing similar discovery times, right? So this slide should actually read AP on PSC, AP on non-PSC, and both times it took less than 5 seconds to discover the 6 gig. So you can kind of see when the pings start, and so the summary of this is today we're still recommending 80 megahertz and preferred SCAD channels, but this may change in the future, especially as more clients come out and we understand what client behavior is. If new clients that will come out will behave as well as the clients that are currently out there today.
It might be early because of 6 gig clients, but have you seen better results from the data collected? Do clients on a tri-band SSID go to 6 more?
Yes.
Or do they go better if you put in just a 6 gig only or a 5.6 only?
That's actually a good question. So we're definitely still learning here, but from what we've seen with multi-band SSIDs, you will see like clients will go to 6 gig. They won't always, like, you will see some interband roaming. So you'll see 5 and 6. There seems to be some logic where clients want to prefer 6 gig even over 5 gig, but it also kind of depends on your design. But yeah, we do see clients going to 6 gig. We do see clients going to 6 gig by themselves on the multi-band SSIDs. So yeah, but as as we have more 6 gig deployments, we'll definitely learn more.
A follow-up question: in Marvis, you have a coverage hole sensor capability to figure that out. Have you seen deployments where they just did a one-to-one replacement? You end up with 6 gig holes?
So we haven't seen that yet. There hasn't been, so coverage hole supports 6 gigahertz, but we haven't seen 6 gig specific detections where there's 5 gig, where there's adequate 5 gig coverage and a hole in 6 gig. And one of the things that's, like, to your question around the roaming between bands, we have the roaming SLE and there's a couple roaming views. So it makes it pretty easy to see, okay, this client is actually doing a band. I was going through this with a customer last week where they spun up a new network and they turned on 6 gig and they had just clients connecting, which was cool. Okay, I am almost out of time, but the last thing that I will talk about is one more Wi-Fi enhancement that will be released shortly. And those of you that know, this is, we've been talking about this for a little while, but it's actually coming out soon. So this is streaming packet capture into the Mist UI. So obviously we have a dynamic packet capture feature where we'll automatically take packet captures, but there are times when you want to take a manual PCAP for whatever reason. We've had a manual PCAP for a long time. The enhancement here is to actually stream those packets into the UI as you are capturing. So instead of hitting start, doing whatever you need to do, pressing stop, waiting for the file to upload and hoping you got what you should have got, streaming PCAP will allow you to see right away if you get what you think you should be getting. And the other cool thing is, so instead of think about how you run a PCAP today, right? You might do it from your laptop where you have a single channel, or or WLAN Pi where you have 2 channels to capture on. Or maybe you set up, you have more adapters, or you set up, some APs, but you put them on static channels and configuring them in sniffer mode. What we're actually doing is we're capturing from the data radios while serving clients, and you just set the client that you want to capture, or the APs or the WLANs that you want to capture. You can set some filters. So here I am setting capturing on my phone, and I'm going to capture management frames, EPOL, and probes because I want to see the client connecting to the network. And we will, so once I hit start, I had my Wi-Fi turned off on my phone. I turned it on. It took a second or two to turn on, and then packets come in. So this is the actual client connecting. And as I walk around, it captures the roams. It follows the client. And the best part is, so yeah, you can do some basic filtering in the UI. But the best part is when you hit stop, it will save a packet capture, a PCAP file for you, and you can download in Wireshark and do your full analysis. So it's meant to be a tool that just makes debugging and times when you need to do a manual PCAP, it's meant to make your life easier and just generally more pleasant experience using packet capture. Keith?
You mentioned capturing roaming. If you turn this on and I go roam between APs, do both APs capture it?
Yep.
So your PCAP that you end up could have multiple APs,
yes,
but you've locked on your iPhone's map.
Correct. Yep. And so in the selector there, you can select one client device here, but we have, and actually let me just fast forward. So lovely. Managed to break a video demo. So this was the PCAP that got downloaded. It just opens up in Wireshark. It's a regular PCAP like you would expect with radio tap headers. We can also capture on the wired interface of the AP. So we can capture on wireless or wired interfaces. Same concept. You can capture on all the APs in the site if you wanted to. You can say I want to capture all MDNS or all LLDP from every AP or ARP. And so down here, this is it's basically a TCP dump expression that you can put in your custom expression. So you can put in WLAN ADR2 and put in as many clients as you want if you want to capture multiple clients.
Can you do the wireless and the wired at the same time? And
not today, but definitely something we want to do.
Okay, so it's possible in theory.
Possible.
Okay.
Yeah. So that way you can capture both sides of a radius transaction.
Yeah.
Like that.
Building on Keith's point, are you using the precision time protocol to sync these PCAP captures between access points?
No, we're not. So we are basically, when we initiate a capture, we send capture instructions to the APs. And so they have a filter that they're looking for, and they will send packets to the cloud when that filter is matched. So there's no like the APs get time from the cloud. So they're all synchronized from a time perspective. And when they have packets, they will send them to the cloud and they'll show up in the UI.
Okay, my experience has been that when you try to consolidate those, unless you're using the precision time protocol, the timestamp causes you problems.
Yep.
So
So
that's why I asked.
yeah, so the APs, like I said, should have NTP because the cloud will give the APs a common time. So the messages may arrive at different points in the cloud, but the timestamp of the packet is the absolute timestamp, and that gets reordered when we make the PCAP file and when we display it in the UI.
But you're using the network time protocol, not the precision time protocol.
Correct.
Okay.
So we've heard in the past, Juniper folks say, not only do we have an external 6 gigahertz capable AP, it is shipping. So is that true or is that not?
It is not shipping.
Okay,
Yep.
thank you.